Bienvenidos. Welcome to beautiful Playa Buye, Cabo Rojo, Puerto Rico. Damaris and I's favorite beach, probably in Cabo Rojo. We live really close to it, and it's a great day for a math class outside. Welcome to Learning with Foster. We're going to continue our discussion with real numbers today by looking at them graphically or geometrically. We're going to look at the real number line. Now, I think most of us are familiar with the idea of a line corresponding to numbers. We use it frequently. We're introduced to it early on in our education. But we're going to I won't say look in detail at it, but we'll look at it afresh as if we're almost constructing it for ourselves. We're going to look at the real numbers graphically and geometrically. Now, our goal with this is to organize the real numbers orderly, or some sort of order. Let's look at a quick example. We've been talking about sets, and we've been discussing the real numbers really as a set in terms of sets. And we noted our very first lesson, I believe, that a set S, for example, consisting of the elements 5, 10, and 3, was equivalent to writing it as a set 3, 10, 5. That is, the order of the elements doesn't really matter. This set S is equal to this set S or B or whatever we label it. Why? Because every element in set 1 corresponds to an element in the other set. It's a subset of itself, and it is an equality because they're both subsets of each other, as we've been talking about subsets and set relations. Well, that's perhaps not the most helpful way for us to consider real numbers. Remember, real numbers are a set of numbers as well. In fact, we've talked about some of the subsets of them, namely the natural numbers, or the counting numbers, 1, 2, 3, 4, 5, 6, extending infinitely in the positive direction. The integers, including the natural numbers, 0, and the negatives, extending infinitely in the negative direction. The rational numbers, a fraction, so to speak, any number that can be written as a over b, where a and b are integers, and b, of course, cannot be 0. And then the irrational numbers, those other numbers that have decimal expansions that neither terminate nor repeat. And all those numbers constitute the real numbers. There's a lot of elements to consider. First of all, we've noticed that all of those are sets with the quality of being an infinite set, and there's some order to them. I mean, even the way we explore the arrival of number, the idea of number, with natural numbers used for counting. 1, 2, 3. If we were counting sheep, 2 would represent 1 more sheep than 1. 3 sheep would represent 1 more than 3. So there's some sort of relative relation between the numbers. There's also expressing, as we mentioned, some quantities involved with these ideas of numbers. So we're looking for another way, perhaps a better way to look at some of the identities and properties of these real numbers, rather than simply as a set in which we can rearrange the numbers in any way, shape, or form, because that's not really what the numbers themselves are telling us. They've taken on a life of more than just a character representing an element. These are defined in terms of relation and quantity for the most part. So this real number line will help us as we look at that. The natural numbers, the real numbers, we'll look at the natural numbers specifically, the smallest subset of those, smallest being loosely defined here, has ordered properties. They're relative relations. 3 is relative to 4 as having the quantity 1 more than 4. 5 is relative to 7 as having the quantity of 2 less than 7. So they're relative relationally, and also there's some sort of quantity involved, whether it's we're counting sheep or whether it's we are walking in distance. And I think distance today, we'll use that example of measuring quantity, will help us as we look at the number line and some of the benefits and reasons for it. So a number line will help us express this fact or this set of properties that we've already noted. Again, to repeat myself, to reiterate one of Damaris' favorite words, the relative relation between the numbers and the quantity associated that in part define what those numbers are. And we are going to use, for example, the idea of distance today. So a number line helps us express all of that. All of those properties that are intrinsic with the idea of number as we've been talking about the real numbers. So what is a number line? Well, let's consider each portion of them. The line itself, we won't be overly formal with our geometric a description or a brief definition, but we could describe a line, and for our purposes here, we'll just simply speak of a line as being a continuum of points. Well, what is a continuum of points? Well, a point, again, without being overly specific, would be a dimensionless dot. A continuum of them would be a series of one dot after another. Now, again, remember they're dimensionless, so this forms a continuous line. A continuum, a line where any given spot on that, say for instance here, any arbitrary spot would represent a point P. Any point P. No matter where you hit, there's not going to be in between. Any spot is a point P on the line. We talked a few lectures ago about the idea of, I believe we were talking of the natural numbers or the integers, where they have discrete quantities. That is, and I liken this to going up a staircase. If you're on stair number 1, and let's say it's a foot off the ground, you are 1 foot off the ground. If your staircase is consistent as it grows, you'll either be 1 foot off the ground on stair 1, 2 feet off the ground on stair 2, 3 feet on 3, because you can't stand in between. It's a discrete quantity. They are, and in that case, each quantity goes up the same amount. Well, a continuous quantity is not so much like that. That's as if it's more like an escalator going up. You could be at any given height at any given time. A number line, or a line as being a continuum of points, allows for this continuous quality. Not simply you're either here, we'll label this point A, or point B, but rather you could be at any given point in between, because the line itself is a continuum of points. So the number portion of the line, again the line we're describing as a continuum of points, the number portion for what we are doing, for the context in which we're dealing with, is the correspondence of numbers to points. So we looked at this, maybe I should kind of mark this off. This is our little working example we're going with here. This is a number line we're constructing. So any given points, in this case we have A and P, the correspondence of actual numbers to those points is what we're talking about with a number line. Now, the number associated with that any given point, P, A, B, Z, whatever, we call the coordinate. So on this little number line we have working, the coordinate is the number associated with any point P. So here's our point P, any given point P. If the number that corresponds to that, just for example, let's say is 7, the rational number 7, then the coordinate is the number associated with that point P. So we're talking about a coordinate line. And this correspondence is what we call a coordinate system. Let's look at an example. Consider this example. Here we have a number line, again the line being a continuum of points. And before we move to the number part, so to speak, let's look at the individual points, or let's consider a few points on here. So one thing to get our minds a little bit playful right now, how many points would exist, say, between point A and point D? How many points would exist between point A and point D? I'll let you think about that. But let's consider this line. Here we have 4 points. We have point A, we have point B, we have point C, and we have point D. Let's see how a setup like this can help us describe these two properties that we notice would be very helpful when we talk about real numbers. One being the relative relation, and 2 being the quantity. And we'll use distance as an example of that. Let's first start with the quantity. How does this number line show any sort of quantitative relationships between these points? Remember, we're not even dealing with numbers yet, these are simply points. But as we talked about, there's a correspondence between the points and numbers. You can think of a number as a point on the number line. Let's consider points A and B. They are a distance of approximately this length of chalk. We'll call this length D. And a way we can denote this is we can say D, standing for the distance of points A and B, we can say are equal to the length of my yellow, or amarillo, if you're watching Damaris' conversational Spanish, chalk. Okay, so that's a quantity. The distance from A to B on this particular number line, we're setting this length of chalk as our unit distance measurement. So the distance of A to B is equal to this. Well, we notice that C and D are as well. So what we could say is the distance of points A to B is equal to what? The distance of points C and D. And I didn't mean anything by lowercase here and capital here. It just kind of happened without me thinking, so don't think anything into it. All right, see, notice just by having these points arranged on a number line allows for the possibility for us to define into it certain quantities. In this case, we're looking at distance. So we can see, without even numbers being associated, that the distance from A to B is the same as C to D. One could think of numbers and say maybe the distance from 1 to 2 is the same as the distance from 6 to 7. In that case, one natural number unit. Or the distance between 0 and 5 is the same distance as 10 to 15. In that case, 5 units of distance. So we can see how this line helps us account for that. Well, what about the relation here? B to C, the distance of B to C is equal to twice the distance of my yellow chalk. Or in other words, 2 times the distance of A and B. Or again, in other words, 2 times the distance of C and D. So we're able to note and denote and keep track of certain quantities based on points on a line. Okay, so we can see that the number line allows for us to talk about certain quantitative properties between points, relating that to numbers as we're looking at a number line. So a number line is very useful in that way. Well, how about the second portion? How about relative relations? And as a side note, we'll have much more to say about distance in a few lessons. We'll look at distance a little bit more formally and have some fun with it. Right now we're just kind of loosely using our familiarity with distance. But how can a line like this, and a continuum of points and certain points on that, describe any relative relations to each other? Well, we can say that B relative to A is my right, I guess it would be your right as well. So B relative to A is in the right direction of A. Now combine that with our quantitative understanding, we could also say that relative to A, B is 1 unit to the right of A. We could look at point C and say that point B is to the left of C. Combine that with our quantitative understanding, we could say that C relative to, or B relative to C is 2 units to the left of C. That's very helpful, right? Well, you know what would be even more helpful if we think about, say the integers. Remember how we talked about how there's positives and negatives? If we could establish some sort of direction to help us with these relative assignments on the number line. Well, of course we can do that, and conventionally what we say is the number line increases in the positive direction as it moves left from right. So a corollary of that, of course, is as you move to the left or from right to left on the number line, the quantities increase in the negative direction. So what we could say is that point B is moving in the positive direction relative to A, or another way to say that quantitatively is B is greater than A. Now, who feels like writing B is greater than A? I sure don't, and I'm sure you're very familiar with the symbol. So what we can do to denote that is we can say that B is greater than A. And this symbol is the greater than symbol. It simply means that, I don't remember if it was second or third grade or whenever I was introduced this, it's always stuck with me, but this is like an alligator mouth, and it's going to open and eat the larger number. So whatever the open end is, whatever letter or number is associated with the opening mouth of this, that means it's larger. The alligator is going to eat the large portion, not the little one. However you want to remember, that's fine, but that's the way to remember it. The open end of this is saying that the number to the left of that, B, is greater than A. Well, what if we want to speak of things being less than something? What if we were describing the relations of B to D? Well, B is not greater than D, B is less than D. So the way we denote that is, again, you guessed it, the symbol, but in reverse, because we're speaking about B is less than D. So this symbol here we read as less than. And again, see that the open alligator mouth is eating the larger quantity. So we read it from left to right. B is greater than A, B is less than D. So some new notation, or probably reviewed notation, but useful notation. But you can see just having a number line with points, how we are able to say quite a lot about points. We haven't even really gotten to numbers yet. We've been using them, or we've been interchanging them somewhat, but we can describe points in relative relation, and if we're consistent with our measuring, we can describe quantities as well. We can say that B is less than C, less than D. We can say that the distance of B and C is twice that of A and B, or C and D, etc. So let's quickly list some of, using our new notation, some of the relations between these 4 points. So we've already done B with respect to A and B with respect to D. Let's see what you guys help me out. If we're describing the relative relation between B and C, what would be the appropriate way to denote that? Well, again, remember our number line we've established conventionally is moving in the positive direction as we move from left to right. So since C is to the right of B, that means it is increasing in quantity, right? So B is less than C. Very good. Let's just do all of the relations. How about A? How about A with respect to B? What would be the appropriate symbol? Well, A is to the left of B, so A is less than B. How about A to C? Again, A is to the left of C. C has a relative relation in the quantitative greater end than A, so A is less than C. And similarly with D. We did our B's, let's do our C's. C with respect to A, C is greater than A. C is also greater than B. And perhaps you're putting in your mind already some ideas with subsets and items like that with some of these relations. And C with D, C is less than D, because D is to the right of C. C is greater than A and B because C is to the right of both A and B. And again, as we move farther to the right on our number line, the greater the quantity is associated with each point. So D, well, we can look at this and see D is the farthest in the positive direction of any of the other 3 points. So D is going to be greater than, of course, A. D is going to be greater than B, and I should be consistent with my capitals. Apologize. D is greater than C. All right, let's use what we've learned to begin to a little bit more finely tune or construct our real number line. We've looked at some of the benefits of a number line with any given point where that number line can express and relate certain qualities, namely relative relation and quantity of some sort. We've been using the distance between 2 points to denote that. So let's turn now to not just an arbitrary set of coordinates, although we haven't been entirely fidel to that, but let's look at the real numbers in particular. Let's begin to not just label points, remember, but we're going to correspond numbers, namely the real numbers, to those points on the number line. And again, remember, we can think of a number as a given point on the number line. So, where to begin? Well, I remember the first time I traveled somewhat far and somewhat being on my own. I ended up in the airport in Paris, not knowing French and barely knowing English adequately at that point. But I got off the plane and I had to change, and I had never really flown much before, and so I didn't know where to go at all. There's a huge airport in a language I didn't understand, in a way I've never really traveled before. So I looked around and I found a board that was very comforting. It had kind of a map of the airport, but even that's somewhat overwhelming. But once I saw this little red star and an arrow that said, "You are here," it allowed me to say, okay, I'm here. That is relevant to both relationally and quantitatively to, let's say, oh, this airport shop A. I am close to it. I am to the right of this shop, and it's only one store down. All right, I need to get over here. Well, I'm able to see now where I am relative to it distance-wise, and also some sort of quantity space-wise. So before we do this, we need some sort of red marker, a comforting red marker, an origin, so to speak, that says you are here, and we can base everything else, all of our other numbers, kind of from that origin, and we'll call it the origin. So let's find point O. We'll call point O, and oftentimes we can denote this as P for point, and whatever our point is, oftentimes there'll be a number in parentheses. There's a variety of ways to do this, but we'll just stick with this. Or we can just say, for a little bit simpler sake, O, the point O, is equal to, we'll call it the origin. Or in other words, from this point, we will build all relations relative to it, both in quantity and direction from this given point. So let's think about our real numbers. What would be an appropriate or a helpful number out of all those real numbers, that infinite number of real numbers we have, that would kind of be a natural good starting place for an origin? Let's start with the point perspective, I guess. As far as a point goes, remember this is a continuum of points, so we can choose any arbitrary point as our origin. Let's just say this point will be, this is point O. But we want to form a coordinate system by relating a number to that point O. So what would be a nice number from the real numbers to equate with the point O? Well, let's think back kind of how our numbers developed. Let's think back to the integers. In a very important sense, we have positive numbers, we have negative numbers, and then we've got that one number, 0, that is right in between those. So 0 sounds like it could be a great natural origin, right? Anything, we've already talked about how on our number line, if we're moving from left to right, we're moving in the positive direction. If we're moving from right to left, we're moving in the negative direction. And I put my arrow the wrong way. So our integers kind of have that built into them already. We've got the negative numbers, we've got the positive numbers, all in relation to what? That point 0. So let's let O be 0. 0 is the origin of our real number line that we're constructing. Now in this case, the letter and the number look strikingly similar. That won't, of course, always be the case. And we could arbitrarily label, we just used O to stand for origin, we could label this P, Q, delta, whatever. But point O, our origin, we are assigning the value or the number 0. So we've got a place to start. We've got an origin, and from now we can construct relative relations, namely something is either greater than 0 or less than 0, or positive or negative, and also the distance, the quantity from 0. Something may be 5 units in the positive direction from 0, or 5 units in the negative direction from 0. That sounds like it could describe all of our integers, right? Which of course also includes the natural numbers and the whole numbers if we're using that subset. So from our number line, let's begin constructing that. Now, when we think of counting, we talked about this in a previous lecture. that the difference between one object and two objects is that object. So the distance between 0 and 1 will be the same as the distance between 1 and 2, and the same as the distance between 2 and 3, etc. And also in the negative direction. The distance between 0 and -1 will be the same distance between -1 and -2. Got an ant on me. So we have to keep that in mind. We won't be able to do that exactly, but we'll approximate to represent what is in actual. So if we're moving in this direction, these will be positive integers. 1, 2, 3, 4, 5, 6, 7. Okay, that's not even close to all of the positive integers, is it? So we're going to have to expand. Baby, I guess we're going to have to get a few more boards and staple them across here. But wait, that wouldn't do us much good, would it? Why? Because these go on infinitely in the positive direction, right? So we used ellipses to denote that in the sets earlier. We can do something similar here. These arrows at the end of this number line represent that the line goes on infinitely or indefinitely in each direction. The difference between a line and a segment or a ray. So, in other words, these numbers continue at this distance or at this same quantity on infinitely far in the positive direction. So this number line extends infinitely far in the positive direction. And this symbol we can use to stand for infinity. Now we're not saying this is a number. This is not a number. This is saying that this line extends infinitely far. So the same thing in this opposite direction. We have -1, -2, -3, -4, -5, -6, and it extends it infinitely far in the negative direction. So this is working great. We can look at this and not just see it as a set with elements that we happen to be writing in order, but we can see that this is built into the definition and understanding of what this real number line is. It allows us to speak in terms of relative relations and quantitative properties. We can say that something is less than or greater than another number or another point. We can say that that number or point how much less than or how much greater than. It allows us to speak of relations and to qualify those relations quantitatively. We can say that -4 is less than 2. Well, how much less than 2? Well, it is 1, 2, 3, 4, 5, 6. 6 units less than 2. So this works great to express the natural numbers and the integers. Well, what about the rational numbers? Remember, a rational number is a number that you can write as a quantity, or not a quantity, a quotient of integers, or a over b, where a and b are integers, and of course b can't be 0. Remember, those are fractions. So now we're dealing with not a set discrete distance, but portions of that distance. Not necessarily a full piece of chalk, but a portion of that chalk, a half of that chalk, a third of that chalk, or a chalk and a fourth, or whatever. So can we represent any given rational number on this number line? Well, yeah, of course, because remember, this is a continuum. Anywhere one places, there is a point. So this point can represent any number. So wherever a rational number fits in between one of the integers, that can be represented by a point. Now, our technology of a blackboard may limit our precision as to how close we may, for example, be able to plot 3.5. We may not be entirely in the middle, but if our precision grew and grew and grew, we could definitely point, there would be a point that represented, that we could correspond to 3.5, or a rational number. So any rational number, there is a point on the real number line where that can be plotted. Again, if we were hoping to plot -4 and a third, well, here's -4, a third. Remember, that's one of those repeating decimals, 0.3 repeating forever. Could be graphed right there, and we can see that. So you can see where this number line allows us to visually, pictorially look at in a different way than our sort of Venn diagram way that we looked at real numbers. Remember, we looked at real numbers pictorially that way as far as how the subset relations are. But in other important senses, by looking at the real numbers as a number line, this really tells us a lot more information in some important ways. It allows us to see, with respect to relative relations and quantity, what all these numbers look like relative to the origin or relative to any other arbitrary number or point. Very handy. Well, what about the irrational numbers? Remember, those are the ones that they're real numbers, but they cannot be represented as a rational number or in the form a over b, where a and b are integers. And remember, the decimal expansion of that went on forever without ever repeating. Well, again, no matter where one finds a irrational number, there is a point on the continuum that can represent that. So in the case of pi, would be somewhere right in here. 3.14, blah, 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 on and on and on. So this number line, the real number line, allows us to graphically plot, visually look at, but also think about and therefore find identities in which every real number corresponds to a point on that number line. Now here's an important observation that we may have made already, that you may have made already by looking. We'll notice that every number, every real number, corresponds to only one point. In other words, the number 6 only corresponds to this point. We could label it P. 6 does not correspond to this point B. 6 corresponds to this one and this only point. Every real number corresponds to a point on the line. Every real number has a coordinate on the line, but every real number corresponds to only one point. That's part of what we mean by these numbers. The relative relations and the quantity, the distance between these are what we mean when we say 6. Let's look at an example. All right, let's do an example together. Let's look at the points. F is equal to 5, G is equal to negative 3 over 2, H is equal to pi, I is equal to negative 2.25, J is equal to 4 over 5, and K is equal to negative 3. Let's plot these on our real number line and then observe some of the relative relations and quantitative relations between these points and numbers. So let's start with F. First of all, just for practice, what type of number is F? Is it a natural number? Yes. Is it an integer? Yes. Is it a rational number? Yes, it can be written 5 over 1. Is it an irrational number? No. So 5. Where would point F be on our number line? Well, here's 5. Fairly easy. So our point F we could graph as that. This point F is describing what 5 is, and it'll show us relations, relative relations, and quantitative relations between all other points and their corresponding numbers. How about G? Negative 3 over 2. All right. Is it a natural number? No. Is it an integer? It's negative? No. It is. Is it a rational number? Yes. A over B. A and B are integers. So 3 over 2 would be, if we're looking at halves, we have 3 of those, or in other words, in decimal, 1.5, but in the negative direction. So remember, our number line allows for us to describe things in the negative and positive directions. So negative 1.5, or it is 1.5 distance from 0 in the negative direction, would place it right. If here's 1, here's 2. 1/2 of that would be right in the middle. So negative 1.5 or negative 3 over 2 would put point G right here. Negative in relation to 0, And the quantity of distance from 0 is the value -3/2. All right, how about h? Pi, remember that's an irrational number. The decimal expansion goes on and on and on and on. So therefore, it cannot be a rational or any of its subsets. So where would pi be? Well, we remember, and again, we're going to be limited by our precision to be able to point this. We'll approximately be pointing it, but our number line represents there is an exact point that corresponds to the exact pi, even though we can't pinpoint it exactly with our technology here. But point h would be equal to pi. Pi is approximately 3.14, etc. So 3, if we divided this in 10, 1 would be here. So about right in here would be point pi, an irrational number. Well, how about pi? -2.25. So again, negative is going to be on this side of our origin, 0. How far on this side? Well, the quantity 2 1/4, or 2.25. 2 1/4, we'll put it right here. Is this a rational number or irrational number? Well, it's rational. The decimal stops, it terminates. So it can be written as a fraction a over b, where a and b are integers. How about j? 4/5, a rational number in the positive direction. How far in the positive direction? Well, almost 1. If we were to divide this distance in 5, it would go 1, 2, 3, 4 of those. And right here, we have point J. Now, K is -3. That's a fairly easy integer. We have an exact spot picked out already. So now let's, since we've plotted or we have graphed these points on this coordinate line or this real number line, let's take a moment and look at some of the relations that we can see, relative relations and quantitative relations between these various points. We won't look at all possible combinations, but let's just pick a few. Well, let's say pi is an irrational number and j is a rational number, and we want to kind of have an idea how they relate to each other. Well, we can look at this and we can note, for one thing, pi with respect to j, is pi larger or greater than j, or is pi less than j? Or in other words, what is the relative position relative to pi? What is the relative position of j relative to pi? Well, here's pi. J is to the left of pi. Remember, our number line tells us that it is increasing in the negative direction, so j is less than pi, so pi is greater than j. And remember, the opening goes towards a larger number. So this number line, we can see that pi is greater than j. Well, how much greater? Well, this distance, this much greater. And we could put a numerical value on that. We won't right now. We're just kind of looking at pictorial relations. But pi is greater than j, and it is this much greater than j. Well, pick another one. Dama, pick two letters of these 2 points up here.
F,
F,
H,
and H. Let's see what F's relation to H is. Where is F? Here's point F. Is F greater than or less than H? Well, here is... Did we miss H? No. I'm sorry. I labeled this by what the value. This was point H. Wow. All right, point H. So let me switch that here. We won't go back and record that, but we're dealing with points. All right, so point F and H. F is to the right of H. As the values, the quantities are increasing, we know that F is greater than H. Well, how much greater? Well, 1 and almost 2. This much. And again, we could put a numerical value on that. We're just kind of looking pictorially at these. All right, very good. How about J, or we already used J. How about G and F? G is on this side. F is over here. So G is less than F. Well, how far? Again, this quantity of distance. Let's do kind of a tricky one. Let's look at points K and G. Let's look at K and G, and I think this will be our last one we look at together. You're invited to kind of go through these and see how they all hash out individually. But let's look at K and G. Let's look at the numbers first. K is -3. G is -3/2, or -1.5. Now, 3 is a larger number than 1.5, right? So it's pretty, we could see where we could get confused and think that K is larger than G. It's not, because this is negative, like you're owing somebody $3, where this one you owe them $1.50. But you can see where looking at the numbers you might get confused. Well, this number line really helps us avoid that error, because we're looking at the relation of points. K and G, K is farther in the negative direction than G is. So K is less than G. Even though the number associated with K, 3, looks larger than 1.5, the error in that is that they're both negative. Here we are a distance of 3 units from our origin, where G, we are a distance of 1.5 units from our origin. So you can see how the number line not only accurately can describe the real numbers, all real numbers, but also can help us avoid some of those possible errors we may make as we're in a hurry or as we're just kind of rushing through things. So let's conclude with this. I'll wrap this up with this, and then you'll have more fun on the homework with some new things that we can work through, and then we'll get together again. Again, your homework will be posted online like it always is. But we can describe the real numbers another way. We've described the real numbers in terms of subsets. We've described the real numbers in terms of decimal expansions, and a few other ways. We've described it pictorially using a Venn diagram. Now let's describe the real numbers in yet another way. We can say that the real numbers are the set of all elements x, such that x corresponds to a point on a number line. Look forward to seeing you next time as we work through this homework together. Have a great day. I'm going to go take a little break from the numbers and go enjoy the water.
Thank you for learning with the Fosters. This is a friendly reminder. Remember that these courses are not for free. For information of the cost of the lessons and how to pay, please visit our website. Thank you so much for being with us.